Okie dokie. We are going to look at this example. I told you I would do this example for you guys. And get a pen up. Come on, pen. Oh, I guess I already have a pen. There's a little green dot. So, scaling the magnitude by 100 gives us these values here. So, the figuring out what omega naught is originally, root 2 rads per second, quality is root 2 over 2, bandwidth is 2. So we're going to look at, that's what we start out with. Now we're going to scale. So we go 100R, which is, and this guy right here, I shouldn't have put this up so quickly. This is for a little later. This is magnitude scaling. The double prime stuff is for the frequency scaling that comes a little later. So this popped up early. Ignore it for now. Ignore the man behind the curtain. We're just looking at magnitudes right now. So the R prime would be 100 times bigger, the L prime would be 100 times bigger, and the C prime would be 100 times smaller, according to these scaling rules, which would keep omega naught and Q and bandwidth all the same. Okay, now we're to the point where we want a frequency scale. And we have a double prime. You don't change R, so we go from this R to this R, no change. We have to divide the impedance by 10 to the 6th. So we turn the henries into micro henries, 10 to the negative 6 henries. And the capacitance, you divide by 10 to the 6th also. So we have 1 over 200 farads turns into 1 over 200 microfarads. The omega prime is going to be 10 to the 6th bigger. Just multiply this by 10 to the 6th. The bandwidth is going to be 10 to the 6th bigger too. So that's going to be 2 times 10 to the 6th, 2 million. And quality is going to stay unchanged in all the cases. Okay, your turn to do this. Now we're going to talk about designing filters. Because we make these circuits to do specific things. That's the idea. So we want low pass, we want high pass, we want filters to pass low or high, we want a band pass or band reject. Now we're not going to get the perfect square waves. Ideal, typical, actual. Passive filters. So this is a low pass. Impedance of the capacitor is really high at low frequencies and goes to 0. So at low frequencies the impedance is really high. So V in pretty much equals V out. And then V out, after you go past the time constant, the V out gets smaller. So here's the gain. Just the voltage divider equation. You can write it like this. So you have one pole at 1 over tau. Omega equals 1 over tau. And you can construct the Bode plot this way. The gain is going to be this. It's going to be less than 1 in all cases. It's passive, no active components. The angle, well, anyway, there's the angle for the circuit, and the maximum gain is 1. The gain at the resonance frequency, or the tau, 1 over tau, gain it here, 1 over root 2, or minus 3 decibels. And the point of this, it's the half power frequency. High pass, just the reverse. This is like an infinite impedance at small frequencies, so you don't get any voltage out, and then it drops as you get to higher frequencies. So it lets the higher frequencies through. Same sort of analysis, except now you have this going on. And it rises and then it flattens out later. Remember when I said when you have omega multiplying a bunch of other stuff, you're going to have 0. The gain is going to be 0. You'll go to negative infinite magnitude and beyond at zero frequency. Okay, let's see. Magnitude 1/tau is the half power frequency again. Band pass, LRC circuit now. This impedance is minimized. Remember, the impedance is minimized at the resonant frequency, so you get the highest amount of signal through at the resonant frequency, and it drops off either below or above the resonance frequency, and we can go calculate all this stuff. It's the same equations we've used before. You've seen them before. So we get this. And we can figure out what omega low is and omega high is, the half power bandwidth. And we have to go back a lot. It's a quadratic equation. Remember, when you set this equal to m at the resonance equals 1, so you set this equal to m squared equal half, and find out what these values have to be at that. You have to solve the quadratic equation, and you get this value. M low, M high is going to be just up here. The difference is going to be R over L. Okay. Band reject. So here's the band pass. The inductor and capacitor are on the top leg of the circuit. Resistors on the bottom. Well, flip it, and you've got your band pass. Same identical analysis even, except now instead of getting the voltage across the resistor, we're getting the voltage across these other two, which of course, now let's keep going there. This illustrates it. The voltage of the source equals however much voltage there is here plus the voltage here, and this passes the band that you want. This rejects the band that you want. And you can tune the band width, by the way. So a lot of times we want high gain amplifiers. You make this bigger, you get a bigger bandwidth, which is what you want sometimes, not all the time. Okay, VL and VC. So looking at the impedance across the capacitor alone, low pass. Impedance across the inductor. Remember, at high frequencies this acts like a really high impedance, so most of the voltage drop is going to be across here at high frequencies. So looking at the VL is a high pass filter, looking at VC is a low pass. So we're talking about designing things. How are we going to design things to accomplish certain functions? So low pass, high pass, band pass. And of course the flip of that is the band reject. Add these two together. Yeah. Sometimes and band reject you want sometimes. A lot of times you tune the band reject at 60 hertz because you want to get rid of it. You don't want it floating around. And there it is. There's the circuit for that. So we get the band reject. So let's take a look at this. Here's a typical circuit that does that. And you have a signal. The little wiggles are what you want. You want the 1000T. You don't want the 60T. And by making a band reject filter design this way, and does it tell us what the resistance is? It does not. So, there it is. There we go. It will depend on REQ, and this is the impedance of these two devices right here. These two devices. Anyway, you get rid of the 60 cycle. You keep what you want. That's the idea of this. So, what is this? First of all, it is a let's see. It is a low-pass filter. We can figure out the RC, do the Bode plot. It passes low, drops off at higher frequencies. Okay, this is a high-pass filter. So it's going to ramp up the tau. This is what's going to tell you where the break point is. Now, tau is in seconds, so let's see. 25 times 20 is 500. 10 to the third, so that's 500 times 10 to the negative third, or 1/2, 0.5 seconds equals tau. So these units are wrong. The tau is in seconds. And then omega is 1/tau, or 2 hertz. You know. That's where it crosses. 2 hertz. 2 radians per second. So we can draw the Bode plot this way. It's remember it was a high-pass filter. So it's going to look like this, and just finding this is the key point. Asymptotic behavior. Okay. Now we have an LRC filter. It's going to be a band pass. We're going to get the gain is the resistance over the impedance. And we go figure out all our parameters. Tau equals 10 to the negative third. Omega naught is going to be 10 to the third. 2 zeta, remember, is the bandwidth, or excuse me, the quality. We get omega low, omega high. We're going to find the bandwidth of this thing. Yeah, bandwidth. Crunch the numbers, you get this. It's going to start, it's a band pass, so it's going to ramp up, and then we have 2 roots. These are the roots. No, I take that back. Is that correct? No, that's not correct. Oh, okay, let's keep going. So the break frequency is at the 1000, there it is, 1000 radians per second. Low frequency asymptote this is where this is the flat line. This is a band pass. At low frequencies it's nothing, and at high frequencies it drops. And here we're going to have the drop off, 40 dBs per decade. Now, this becomes, so it ramps up. It's a band pass. Ramps up, ramps down. This is a log-log plot, by the way, just remembering that. Decibels are on a log-log scale. And the, let's see, flat line. So these are asymptotes, by the way. Remember, they're asymptotes. The reality is more of a curve, like this. .618, half power low, half power high. Okay. So we're talking about passive filters. This is this recording has gone on a long time now, so we'll talk about active filters next time.